research interests are in this semiconductor for photovoltaic and photoelectrochemical solar fuel generation. And today he is going to talk on this material engineering for solar energy harvesting and renewable fuels. So with this brief introduction, now I welcome Dr. Shukla again and invite for his talk.
Thank you very much. Thank you very much for the kind introduction, Dr. Prasad. It's great to be back here. As Professor Prasad explained, I completed my master's here in 2011. So this place is like a temple for me. It's always a fun to be back here and talk in front of you and also our distinguished professors. So I kept the title of my talk very generic, just to motivate you that how you can use different material systems and all the fundamental research that you are doing towards this broad topic called solar energy harvesting, which is quite a hot topic right now, and also the urgency that we have right now because of the global warming scenarios, etc. So I don't think I have to motivate you enough for that. So just a little bit about IMEC, where I work. What IMEC is, it's basically a public-private research entity, basically working predominantly on microchips domain, like making semiconductors and microchips, etc. And it has a very strong foothold in this domain. It's also called the microfab lab of the world. So 75% of the funding in fact comes from the industry, and the rest of it comes from the government, local government, and some local support. And there's a world-class clean room there, which is, as you can see, 12,000 square meters. It's quite huge. And there are more than 5,000 employees working there from over 100 nationalities. In fact, we are celebrating 40th year this year. So having said that, since they work on microchips, energy is also a very vital component that they also focus on that. And this is where the energy research facilities are located. So the IMEC headquarters is located somewhere close to Brussels. As you can see, Leuven. So that's the IMEC headquarters where all the microchip or semiconductor research happens. And if you go to the northeast, close to the Netherlands border, you have this center called Energieville, which is a newly inaugurated center, relatively new in 2018, where all the energy research is located, and that includes solar cells, batteries, power to molecules, green hydrogen, power engineering. All that stuff happens here. And this is also unique in the sense that traditionally this place was a coal mine. And now they want to convert this place from a coal mine to a symbol of green energy. So the whole city is being developed as a sustainable township concept. So this is where I sit, right there, the black building. And as you can see, this is the coal mine, which was previously, and it is now preserved as the National Heritage at the moment. It is also part of UNESCO Heritage. And the whole city, as I said, they are trying to power the whole city basically by renewables. All the heating, cooking, and the electricity that will come from renewable sources. So that's the concept. And Energieville is actually a collaboration involving several entities, and that includes the university, which is here in Leuven in Belgium. You have the University of Hasselt and two research institutes, namely VITO and IMEC. So all forces combined together, they come together for one common goal, that is the energy research. Now, I will not go into the detail of what broad activities that we do at Energieville, but I'm going to go condense directly on the solar PV part and solar fuels part, which I will explain in a moment what that is. Now, we have some state-of-the-art tools facility for PV production at Energieville site, and this lab is not like a very fundamental lab. The goal of this lab is really to pilot things from lab scale to something big. So that's why our equipments are also big. As you can see, the evaporation chamber, where we can literally deposit over this large area, 35 plus 35 centimeters square. Just to give you an idea, it's about this big. So imagine you can fabricate a solar cell or solar panel in your lab, something this big. That's quite remarkable. And there are also solution processing enthusiasts who do slot die coating, also on the same scale. We have blood coating, and we also do laser scribing to make different patterns so that we can connect one solar cell to the other. And we do laser scribing. And there is also module encapsulation, because eventually we install these panels or modules on top of the roof for outdoor testing. And before testing, we actually encapsulate everything inside this inert ambient, which is a glove box, nitrogen-filled glove box. This is the huge area where everything is located. So as you can see, it's 1500 square meter place where you have PV module research, battery research, thin film, supercapacitors, and green hydrogen. Everything happens. So this factory-looking place is actually a lab. And as you can see, there are no walls in between, just some demarcations. This is purposefully done to enhance the synergy between different groups. So when you have to say hi to the battery folks, you don't have to knock the room, but everything is open, so the collaboration becomes seamless. Then there are some module assembly and testing facilities at our center. We have this lamination. So when you complete your solar cells, go from cells to modules to panels, we do this lamination, and everything is automated. We are cutting down on the human involvement because the throughput is always a key when we talk about the industry. So throughput is, because of that, everything is automated. We have this big solar simulator. When you deal with the big size of the panels, you also have to have a solar simulator, which has to be that big at least. And then we have reliability testing, which means you subject your device to high temperature, high humidities, or combination of that, and check how it performs over time. That's reliability testing. It's very important. And then we also do outdoor testing. So these pictures that you see are actually from the rooftop of our labs. Some of these panels are actually installed in Cyprus. One of you are actually working there as well, I believe. And as you can see, some of the panels are actually hanged on the wall also. And this is all for the reliability testing and real life practical testing of these modules. Now these blue looking cells might give you an indication that we are working on silicon. All these blue looking panels or darkish blue colors, they are typically silicon, but we have pivoted from silicon to something else, and that's where I want to give you a motivation of the broader picture. Solar cells today are not just meant for green electricity. They have a larger impact, which is when it comes to defossilization. So all the energy needs that we are getting in the form of fuels or electricity, some way or the other it is coming from fossil fuels, and that is a problem. We all acknowledge that. We use terms something like decarbonization, which I feel probably is not the right term to use because we are all made up of carbon, so we cannot completely decarbonize everything, but the key is to defossilize. So the basic idea is that you take the energy source, the most abundant energy source that you have, which is available from the sun, combine it with the most abundant resource that you have in the planet, that is water, and combine it with the biggest problem that you have in the planet, which is CO2. So the energy comes from the sun, the water gives you protons, right, because it's H2O, and then if you try to include that proton inside the CO2, give some energy, you can convert CO2 to something useful, which is hydrocarbons. The cars and the bikes that you drive are all powered by hydrocarbons. So the basic idea is to convert the CO2 to something useful. Not just hydrocarbons, you can also make nice chemicals which are useful in hygiene industry or pharmaceutical industry. That's where solar cell also comes into the picture. So it has a higher consequence now. In the future, this is how the economy is envisioned, that the future would look like. You have this factory which is emitting flue gas, which is a mixture of CO2 plus other nasty gases. And then you have these renewables, which are not biased towards solar PV because I work on PV, but you can have other renewables as well, like wind, or even nuclear is on the horizon, but I will not talk about it. So imagine a device which takes up these flue gases, takes the energy from renewables, does something, this black box does something. PEC stands for photo electrochemical. So it does something, some chemistry, and converts these CO2 and water molecules to something called chemical feedstock, which can be used in different industries, or also make fuels that can be directly used for our household applications, and even you can store these fuels. So it also solves the storage problem, because when you have a solar cell, it is only going to work when the sun is out. But in the night, what will happen? You need to create something that you can store as well. So you store the energy of the sun in the form of chemical bonds, which are fuels. You can store them, and then you can use it back. Then you can capture, this way you close the carbon cycle. That's how the future economy is envisioned. Well, how you can do it? So there are several ways. When I'm only talking about photoelectrochemical ways, there are 3 ways you can do it. One is the PV electrolysis. Electrolysis is something not very new. In fact, it has been done for almost a century now. So you take a battery or any source of energy and provide enough potential that you can split the water. Because water is a molecule, there is an energy associated to break these bonds, and these energies are known because you know the free energy. So the free energy is close to, let's say, 1.23 volts thermodynamically. If you can provide that energy, you can split the water molecule. You can also do the same thing with the PV because now the energy is coming from the sun, so everything you do renewably. So that approach is called PV electrolysis. And as you can see, anode and cathode, where the cathodic chemistry, which is the reduction chemistry, anodic chemistry, which is oxidation chemistry, can occur in the dark. And that's why I have indicated in the black color. This is PV electrolysis. This is most advanced. And right now, all the economies in the world are actually focused on the first approach because it's pretty much advanced. Because PV is developed, electrolyzers are developed, this combined both. The second one is more in the fundamental level, where you take semiconductors, where you do this chemistry photoactivity. You use the energy of the sun, take the semiconductor, you generate electron hole pairs, and these electron hole pairs, you expect the electron to do reduction reaction if the energy is right enough, and the holes you do the oxidation reaction. So that's called photon to molecule. The first one is power to molecule. And it's also termed artificial photosynthesis. This is what nature also does in the form of leaf, but it makes glucose something else because the goal of the leaf is something different. The third one is also photocatalytic. I will not talk about it, I have very limited time, but this is also another approach. So there are two key elements, as you can see. One is the PV, solar PV, and the second one is photoelectrode. Both involves materials. You need to have materials that you can construct good PV device. You need to have materials for which you can make good photoelectrodes. So I will talk about these two and give specific examples. So let's talk about the IMEX PV research in general. So it all started quite a long time ago in 1984 when the founder of IMEC, who was Roger van Overstraten, also got the first Becquerel prize, which is a very prestigious prize in the PV community. Actually kicked off this activity with silicon modules, and IMEC used to be and still dominates silicon PV as such because there were a lot of processes that were developed in IMEC which are still used at the industry level. So all the processes were discovered long back in 90s, and then after that there were several spin-off companies, some very successful stories, some not so successful ones. Then there were some passivation schemes to take really the primitive silicon cell, make it to more advanced, something called PERC silicon or TOPCon silicon, which are the state-of-the-art silicon solar cell devices. So this was more or less the journey. And in 2017, something happened. In fact, 2015, something happened, a revolution in the field of PV, then halide perovskites came into the picture. These are hybrid materials, very low-cost ones. I guess some of you might have already know about this. So also started working on that, and now we are focusing also on making silicon, combining with this new material to make even higher efficiency devices. These are called tandem devices, and that's when the energy bill was also formed. Just pictorially, I want to show you what we do in our lab. So these are halide perovskite cells. We started with very small cells, as you can see, 0.13, very small area, very high efficiency, 21, more than 20%. Then we scaled up from that scale to 10 plus 10, which is 100 centimeters square. We're still maintaining efficiency more than 15%. That's quite nice. But as you can see, these films looks okay, but they don't have functionality, as in they are not transparent. So the goal is to put them on the windows where you can see through a little bit. So then we started also working on transparency. So here you replace the top electrode, which is typically copper or something, with ITO, which is transparent. You also have a very large device with decent efficiency, 13%. Flexibility is also one domain where we are focusing on. As you can see, this is a flexible module, fairly large scale. And then we also work on this reliability. So all this data was done outdoor in the real life conditions when there are fluctuating solar conditions. And this data is coming from Cyprus. Okay, it's actually published. You can have a look at it. And there was some skepticism in the community that perovskite cells are not so stable, which is to a certain extent true, but it was not that bad as it was thought it to be. So you can see it, but 2 years data indicates that these cells do not die. So they just lose like 20 or 30% efficiency, their original efficiency, but they survive more or less. The key is that you have to passivate them and encapsulate them nicely. The second one is also thin film solar cells, CIGS type, so copper indium gallium diselenide. These are thin film semiconductors. We also work on that and get efficiencies close to 15%. We are also doing something recently in 2D materials. Tungsten diselenide can grow it on silicon at fairly large scale with very high lifetime. So this is quite an interesting result. So imagine a 2D layer which you can grow at fairly large scale, still maintaining the high lifetime. So the material quality still remains pretty good. So this is something very recent. We published in fact this year itself. All this data that I'm showing belongs to the team. So when I say we, it's not that me who is directly involved, but it's the team of the energy group. Then there are different material systems we developed at Energywell for photoelectrochemistry. So as you can see, chalcopyrite, band gap of 1.7, castorites, wittichinite, stibnite, which is antimony sulfide, is also quite interesting. It's a layered material, quasi-1D. Carbon nitride, very cheap one, there is no metal involved, and then perovskite. So all these material library that we have developed in our lab, and we're still trying to screen some of them, which one stands out, let's say in 5 years, which one goes to the next stage and which one we simply dump for the other activity. Now, let's talk about...
You were showing in the board, huh?
This is the SEM image?
Huh?
Yes. Yeah, please excuse me for not putting the scale bars over here, but this is SEM image. Different morphologies. This one is particularly very interesting because this is coated on silicon. So the blue is silicon, and on top what you see is antimony sulfide. So it's a monolithic tandem that we developed very recently. Let's stop a bit and try to understand how fundamentally everything happens. So first thing, when you look at, you have to first see the sun. So which means I'm talking about the solar irradiation. It's a black body radiation typical. And then you have some certain nuances. It's essentially the gases present in the atmosphere. You have this. Now you have the materials in your hands. So you know the band gap of the material and absorption, etc. Now let's imagine you have a material which has a lower band gap. You put it somewhere here. It will absorb all the light below that. So for example, if your band gap is low, all the light below that energy will not be absorbed, but above that energy will be absorbed. Okay? But if you have a lower band gap, the energy of the photon is low, so the overall output will be low. If you go to this spectrum, you take a semiconductor which has a wider band gap, something like this, and the energy of the electron and holes would be high enough, but all these photons will be wasted. So you have to get some sort of a compromise, and the compromise is somewhere at 1.4 electron volts. But still quite low. So you see, if you have a band gap too low, you will have thermalization losses. So all the energy is lost in the form of heat, photons. And if you have a semiconductor which is too wide, then a lot of photons will just pass through incomplete absorption. Now, then let's say you have this device and you create electron hole pairs. The maximum voltage that you can get is not the difference between the conduction and valence band. It's not true, because you have something called quasi-Fermi level. So imagine a p-type semiconductor where the Fermi level is close to the valence band. As soon as you shine light, you generate minority carriers, which are electrons. Now the distribution of electrons and holes cannot be given by one Fermi level because the picture is out of equilibrium. So you need to have these quasi-Fermi levels. The difference of these two actually gives the maximum voltage, not the conduction and valence band. So this is a quantity called quasi-Fermi level splitting. You can actually determine it. Even here, in the spectroscopy lab that I have seen, you can actually determine this, and I'll show you this in the next. So in order to absorb all the photons, you need not just one but two semiconductors. Let's say 1.7 top cell and 1.1 bottom cell. This way you cover the entire spectrum. So this is a tandem cell concept. 1.1 eV is actually silicon. You don't have to think about any new material. All you have to think about, do we have a material which is 1.7 electron volts band gap? Perovskite is. But do we have others? Perovskite has a problem of instability. Now, if you make a solar cell is actually nothing but a diode in the dark. This is how a typical current voltage characteristics look like. This is the dark pair. You see it resembles like a diode, and everything kicks off around that particular voltage. So this is the majority carrier current. Now when you shine light, what you do, you generate minority carriers. The curve simply shifts up by this amount, which is the photogenerated current. And now these are the metrics which are important for a solar cell. This is the short circuit current density, open circuit voltage, and how square that curve is. This is called fill factor. How much it is deviated from the ideal box. It will never be a box, by the way, but it gives some curve. This is the maximum power point. Power point means multiply voltage and current, that's your power. Somewhere here the power is maximum. So this is how you read a typical data of a solar cell. The same thing, now let's imagine something very interesting. The same electrons, when they flow in the circuit, they constitute current. But the same electrons you can use to drive these chemical reactions. So if you put the water molecule here, and if the energy of the electron is right enough, it can reduce this species of proton to hydrogen, green hydrogen, that's what we call it. And if the energy of the whole is right enough, it can do oxidation reactions, it can convert water to oxygen. And you can replace this water with some other molecule and get other chemicals. How to read that? Typically, if a reduction reaction which is happening, you get a negative current. Oh, there you go. Combine it with the oxidation, this part, you get the positive current, which is anodic current. This is typically, when you go into the literature, you will find these curves. How fast they go determines how best your device it is, and how less voltage you need to do this reaction also is important. You don't need very high energy, but some things you cannot reduce because of the thermodynamics. So 2 volt is the typical energy you need to split the water molecule or CO2 reduction combined with water oxidation. Okay, same device concept. It's just the way you use your electrons defines your final result. I'm going to tell you a story about a semiconductor which has a defect. A semiconductor without defect is boring. It becomes interesting when you have defects in it. So today I'm going to talk about copper indium gallium disulfide, which has a band gap in the range of 1.5 to 2.4. It's a range because depending on the quantity of gallium, you can change the band gap. And I want a band gap close to 1.7 because I want to make a tandem device. So the first device I'll talk about is a solar cell. Here you have electron extractor with a band bending and all that. And then the second is the same semiconductor you can use to drive chemical reaction. Same semiconductor. So let's see. You start with this. So how do you do alloy? Essentially, you have 2 points where you have species copper indium sulfide, certain band gap. Gallium is smaller in size, so you replace indium with gallium. You seamlessly change the band gap. On the y-axis, you can see the band gap is changing. There is a certain going because of the disorder, but you can go from 1.5 to 2.4. I want to stop somewhere here because here the band gap is 1.7. Because I'm hunting a semiconductor which is close to 1.7, so I will stop it there. But what happens when the band gap changes? Either the conduction band goes up, or the valence band goes down, or both can change. So this is something we don't know, so experimentally we need to know that. So for example, this is the valence band maximum, and then your conduction band start increasing because you are putting more and more gallium. Some of the shallow defects means the carriers that constitute to the current, some of these defects actually become deep because the conduction band keeps on increasing, but the deep defect does not move when the bands move. So what happens? Here everything is fine, but as soon as you are here, the carriers just relax to this deep defect and these carriers are lost. So the same defect becomes detrimental when you increase the band gap. Okay? Now, skip that. This is a very profound and fundamental problem. In fact, this can become a good proposal in itself. And let me show you how. When you increase the band gap, and I told you the photovoltaic should scale with the band gap, so it should increase, but it actually plateaus. So you see, when you expect your band gap to increase, the photovoltaic to increase in a linear fashion, or at least, let's say, more or less should follow the band gap. But you see this plateau. You also see this plateau in this CIGSE material, which is the state-of-the-art material from thin film. You see this plateau is coming. Even in halide perovskites, which are very good, try to increase the band gap by alloying or something, you still get this plateau. So something very fundamental happens. And there is a paper here. If you are an enthusiast, you can have a look at this paper, that how a deep defect actually governs all the recombination in wide band gap semiconductors. It forms, you can't do anything about. Well, let's move. How this photovoltage that you get, you can lose. Remember, you need high photovoltage. Now, there are ways you can lose this photovoltage. These are the losses. 2 ways you can lose. by recombination losses. So the carriers that we generate by light, it gets lost either in the bulk or at the interface. So in the bulk, what can happen? You can have this is the more or less conduction band, valence band. These red things are the tail states because of the disorder. Okay? These are like very low density of states, let's call it. So above tail. You can have recombination from these tails. You can have a recombination through this defect which is somewhere in between, which is a wave defect, right? So all the carriers just can come and relax here, and you lose those carriers. So these are more or less bulk recombination. And when it comes to the interface, you have material A, which is your absorber, and then you combine it with the N-type material. So this band alignment actually decides the recombination. So there should not be too much energetic mismatch. So material A and material B cannot have this scenario, this scenario. They should be more or less okay because the electron would like to go seamlessly from one material to the other. And that's where interface recombination kicks in. You can have negative conduction band offsets. Okay, there's a little bit of jargon, but essentially this is your semiconduction band of your absorber. This is your N-type material. If it is low, it's a cliff. The electron loses its energy very fast. If it's above, it forms this barrier. This barrier should not be too high. So you have to do some band engineering at the interface.
These defects are inbuilt or you induce the defect?
Some defects are intrinsic, spontaneously formed because of the virtue of their formation energies, which you can actually passivate by changing the growth conditions. And interface is something they also forms because the way you make the contact with other material. You can passivate them by putting some sort of a passivation molecule or something. Yes. Sometimes you have extrinsic defects. Let's say you did synthesis, but you have chlorine or something coming from somewhere, like a crucible can be a source of aluminum, and that aluminum is doping and making it crazy. These are long stories, but we have less time to talk about. But this has happened in the literature. There's a Nature and Science paper talking about good performance, and all that was coming from the crucible. Okay. So all the research, the stuff that I want to show you today is actually published. We published in 21, which actually gained quite attention also, because this was the highest efficiency report at that time. So the key word here is composition engineering. Let's say I started making the CIGS. How do you make it? Of course, there are several ways you can make it. You can do solid state synthesis, which is quite popular over here. You do solution processing. This was co-evaporation. You take copper, indium, gallium, all individually, evaporate them in the presence of sulfur, heat them at temperature where it crystallizes. It makes CIGS. Now, you can tune the composition. Every alloy or any system can tolerate a certain amount of deficiency or excess. So let's say in the CIGS, that is, I started taking copper out, then it becomes copper deficient. So the property of the system should allow that deficiency to be accommodated, and that is decided by the phase diagram. So if the phase diagram allows you to make a semiconductor with certain deficiency of a molecule, you can do so. I made this copper poor, so you see CGI, which is copper over gallium indium ratio. Roughly it is about how deficient in copper your film is. I also made copper rich film, which is 4 copper excess, and it makes copper sulfide eventually. Okay, everything is clear? So the goal was here to introduce this copper deficiency and see if the material behaves differently. You can also make this semi-transparent, so they are very cool for semi-transparent solar cells. These are on molybdenum. As you can see, these numbers indicate how low you go in terms of CGI, so how copper deficient your films are. So that's a CGI 1.2. So the films are highly copper rich. And you see the morphologies are very different. So composition also decides the morphology. So it's also one parameter that you can tune. So I went from 1.29 to very copper deficient, 0.9. And if you go even more, the phase diagram doesn't allow you to do so. The film will fall apart into different phases. And this is all governed by thermodynamics. It cannot accommodate that much of copper deficiency. Then, with these good old measurements of photoluminescence and quantum efficiency measurements of our solar cells to find out the band gap. PL is something you are very familiar with, not going into the detail, but 2 things I want to highlight here. Why I did 2 measurements, not just 1. This is more of an optical band gap, what you get from photoluminescence. What you get from this quantum efficiency, electronic measurements are more of electronic band gap. They can be different, okay? Now, these are the numbers, copper rich, go for copper poor. More or less, their band gaps were not so different, let's call it. Still in the range of 1.6, 1.59. So they were still same, the only thing that was different was copper deficiency. Same thing we confirmed from copper quantum efficiency measurements, the band gap. Let's look at more detail. Let's say you want to know the deep defects. How can you see deep defects from any measurement? Can you see a deep defect in photoluminescence measurement? And the answer is probably yes, you can see that, but not at room temperature. You have to go to low temperature to freeze those defects. Let's look at this one first, because this is essentially the same thing. This is copper rich film, copper poor film, because the ratio is less than 1. You see there is just one peak coming up corresponding to the band edge transition, which is the band gap of the material. As soon as you make it more copper rich, you see some of these peaks appear at low energy. Actually quite low energy, 300 to 500 electron volts. So these are deep defects, which are present in the copper rich film, but if you make it copper poor, you can actually get rid of them. So composition acts as a knob to tune the defect. Same thing, normalize everything. There are two defects in fact, D1 and D2. D2 is more deep, so this actually inhibits the photovoltage. So you can never get voltage more than 1, because carrier will just jump here and will just make a recombination. So this is one limiting factor. Same thing we checked in the cathodoluminescence. So this is a different technique where you bombard with electrons and see the luminescence. Also see the same defects. Very consistent picture we get. And this is what we did with University of Cambridge. They are fantastic in doing that. Let's look at pictorially. So we also did mapping. So let's say there were two defects, right? One that was a band edge. So this was the band edge emission 1.6. If you map it, spatial mapping, you see when you go from copper rich to copper poor, they get more intense. So your band gap signal improves, which means the quality of your sample is becoming better. Because PL is the indicator of the quality as well. Because you have less recombination essentially. At the same time, if you look at the defect emission, which is the D2 defect, remember, you go from copper rich to copper poor, it gets low. So your defect reduces, your band edge emission increases. That's an indication that you suppress recombination. Right? That's why you have higher band gap luminescence, but you have less defect emission. So this is a very consistent picture. Now, how can you know the quasi-Fermi level split in what I talked about in the first slide? Can you estimate this? The answer is yes. So very fundamental, if you apply the principle of reciprocity or principle of detailed balance, which means in is out, both are same. So the radiation that falls on a gray body and the radiation that comes out from the gray body should be equal. So this is the luminescence that comes out from a gray body, or let's say black body, should be equal to the absorptivity of the sample, absorption of the sample. This is the absorptivity times the black body radiation times the non-equilibrium factor that's introduced. So this non-equilibrium is essentially when you shine light, you generate this delta EF split. This is the non-equilibrium factor. Black body, you already know, this is the relation, this is the Planck's law, and then you plug it everything in that, it becomes a generalized Planck law. So with this, if you know the photon flux coming out, PL, you can actually estimate the delta EF, which is the quasi-Fermi spectrum. The example is here, this is the photoluminescence. Using this relation, fit it, and you can find how much maximum VOC you can obtain. We did that, and look at this. This is the CGI, copper rich region. This is the region where things are copper poor. And the difference in VOC Shockley-Queisser is the maximum VOC you can get thermodynamically. It's called Shockley-Queisser limit. Don't have the time to go what Queisser limit is, but it actually poses a fundamental limit governed by thermodynamics. So the difference of this tells you the loss in the material. The lower this number, the better it is. The more close you are to the theoretical number, the better it is for your device. So as you see, if you go from copper rich to copper poor, the number decreases, and this is actually nothing but because of the fact that we reduce the recombination. And that's why it is happening. At this point, if there is any question, please feel free to ask. Okay? Pictorially, it looks something like this. Fine. Now, so far I'm talking only about the bulk. If you map it, so this is the maximum you can get a voltage that goes to the band gap. This is the thermodynamic loss, which is the Shockley-Poisson loss. This is another loss because this is the maximum quasi-familiar splitting that you get from your photoluminescence. While theoretically this is possible, which means this is a loss, it's called interface loss because this is a bulk measurement and this is the VOC that you measure. Okay, so there are a lot of losses. Eventually you get this number while you should be getting this, while the theoretical limit is this. Okay, so what we did, this is the case of copper rich, but in the case of copper poor, you see this green thing is substantially suppressed because the difference between QFNS and VOC, which is here, is nothing but the interface recombination. Okay, this is material quality loss, this is the interface loss. You want to suppress it. And how did we manage to suppress it? Let's see. As I said, interface is governed by the p-n junction, so the n partner is very important. For CIGS, the n-type partner is cadmium sulfide or zinc oxysulfide. Okay, this is the copper poor regime. You see, VOC that you obtain of your solar cell device is close to the quasi-fermion splitting, which means less interface recombination for zinc oxysulfide. So when we change from cadmium sulfide to zinc oxysulfide, our VOC matches with the quasi-fermion splitting. No loss at the interface. But when you have cadmium sulfide, there's a lot of loss, which is interface, boom, your VOC comes down. It's because cadmium sulfide is not a good part. Same thing in copper rich, if you see, with cadmium sulfide, with zinc oxysulfide, both show difference. So there is interface recombination all the time. Which means copper rich CIGS sample is always dominated by interface recombination. And this tells me, or this tells us, that copper rich CIGS surface has some defect which you cannot get rid of. There is something peculiar to copper rich stoichiometry which we don't understand what it is. And there's some explanation pictorially what happens when you change from cadmium sulfide to zinc oxysulfide. Why interface recombination reduces is because your band changes from cliff to spike. Remember in the beginning I said electron doesn't want to lose its energy. So we change this configuration. So conduction band, the electron doesn't lose its energy, and that's why the interface recombination is suppressed. Okay, I'll skip that part. Now let's look at the charge carrier lifetime. Essentially, you look at the transient, how fast your photoluminescence decays, and if you fit them, and I'll come to that, the nuances of fitting also. You see copper rich sample, green, has a very low lifetime. Well, if you make it copper poor, the lifetime improves, and if you put zinc oxysulfide, which means passivate the interface further, then your lifetime improves even more.